So we've got this little mini unit. I have this section 4.7 from the last chapter that we just did, and then 3.11 from the previous section. They're both more of kind of the story problem. They're a little bit more tricky. So I figured if I pull them out and kind of give them some special attention in their own little unit, maybe they would go a little better. So applied optimization is one of the things that we are going to be looking at first, and then related rates is the second topic in this mini unit. And optimization, to optimize something is to make it the best it can be, I guess. So depending on what category you're looking at, you either want to maximize something or minimize something. So we've talked about finding maximum values and minimum values. That process is still going to be the same. We're still going to be looking for critical points, setting them equal to 0, looking for maxes and mins and things like that. The difference with this optimization stuff is that we need to come up with the equation. We need to come up with the scenario first. So we're going to talk about a general strategy for solving these min and max problems. And so the first thing we're going to do, and it's almost like a story problem. I'm sure in algebra you at one point had kind of written out step-by-step process to how to do story problems. It's similar to that. So a strategy for max and min problems. First, you need to identify all necessary info. I'm going to try to make these bullet points short and sweet. All right, so identify all the necessary info, meaning, like, what are we trying to solve for? What variables do we have? What values do we need? Things like that. Then develop a mathematical model. Develop a mathematical model, and I made this one a double line so that I can include something else. We need things like pictures. I always recommend drawing a picture, especially if you're a visual person. Then you can get a nice idea of what the problem is. Labels. You want to label whatever you can on that picture. Variables. So you kind of like, oh, this is X and this is Y, or let's use H for the height and R for the radius, something like that. And then, of course, functions. You are eventually going to need a function. Okay? Next, find the domain. So you're always going to be trying to minimize or maximize a certain value. So the problem might say something like, what value of the radius would maximize the volume, or something like that. And so like a radius, for instance, its domain, the radius can't possibly be negative. So like its domain would be r is greater than 0, or something like that. All right, so we always want to identify the domain, and that's because picture those absolute min and max problems that we had. We were always given an interval, and then whatever answer we came up with, we could figure out if it was a feasible answer by checking to see if it was in the interval. So just like I said before, the big difference between these problems and the one we had in the previous chapter is that there's nothing given to us. We have to come up with the functions ourselves. We have to come up with the domain ourselves. So we find the domain so that we can see if our answers that we came up with are feasible. Then we identify any critical points. Critical points are the same thing that they were in the last chapter. They are places where the derivative is either equal to 0 or it's undefined. We find the critical points by using this function that we came up with, same way we found before. Again, taking the derivative and either setting it equal to 0 or finding where it's undefined. And then we know whether the critical points are feasible or not because we have this domain that we've already written down. Next, find the max and min. I guess I should say max or min, because in a story problem, you're often looking for one or the other. And then finally, number 6, we're going to interpret and answer. So a lot of times they might be asking something slightly different, so you always want to make sure that you're answering the question. Even if you solve for the variable, you want to make sure that you're answering the question. All right, so we're going to run through a handful of examples here, kind of increasing with difficulty as we go. So example 1, find two numbers whose sum is 20 and whose product is as large as possible. So we always want to start with, what's the necessary info? What are we trying to solve for? Things like that. So find two numbers whose sum is 20. So what we're seeking is two numbers. What we know is what their sum is, and what we're trying to figure out is how to maximize profit. All right, so what we're going to do is come up with this mathematical model. There isn't really a picture that we're going to draw, but we definitely can come up with some variables and some functions. So let's use x as the first number. And then let's use y as the second number. So anytime that you set up variables, you always need to identify which is which. Okay, and then let's use this first part of the sentence. Find two numbers whose sum is 20. So we know if I take these two numbers and I add them together, I get 20. So I've got lots and lots of different possibilities for things that I could add. They could both be positive. I could have one negative and one larger positive number, all sorts of possibilities. And then we want to maximize the profit. So what we are trying to do, our optimization, is we are trying to find the maximum of, and let's do P for profit, which is x times y. So we know their sum is going to be 20, and we want to maximize their profit. We want to make it as large as we possibly can. Okay? Next, find the domain. So let's say that we're going to solve for x, I guess. So we've got these two functions right here. This function right here, this function right here. We call this the primary function or the optimization function. This is the one that we are going to end up taking the derivative of and solving and things like that. But currently we've got two different variables. We do not want to deal with implicit differentiation. We don't want to do product rules. What we do is we take this secondary bit of information and we use it to make some sort of substitution in here. All right, so this one right here, let's sub out the y. So let's say that y equals 20 minus x, and then we can sub this out right here. So the product is going to be x times 20 minus x, because we know that the sum is 20. And so distribute that x, and we get 20x minus x squared. So that is my product function, and then I can optimize that pretty easily because I only have one variable. All right, so a domain for x, I suppose x could really be anything. There's really no restriction that we'd put on it at all, because if you had, if you had a number like 1 million, you could just use negative 999,980, and then the sum would still be 20. So really x could be anything. That's the symbol that we use for all reals. So that is our domain. Okay, so really any answer could be feasible. Okay, next step, identify the critical points. So I identify critical points by taking the derivative. So the derivative of this function right here, derivative of 20x, of course, is 20, and then the derivative of x squared is 2x. So I take this, I set it equal to 0, and when I solve there, I end up with 10. Okay, so the only critical point that I come up with is 10. And so I can identify that as either a max or a min. One thing that would be really easy to do, because I could set up a sign chart and I could do the first derivative test, but the second derivative test is actually super, super easy here. So if we take the second derivative, the derivative of this is a -2. So what that means is that my shape is concave down. And if my shape is concave down, then any critical points that I have must be a max. So I'm going to practice this second derivative test just because it's not really as intuitive as the sign chart test is, the first derivative test. So we'll practice it whenever we can. So it's definitely a max. And so what we want to do is we want to interpret and then answer. What they want is two numbers. So our answer would be x equals 10 and y equals, I plug it into this function right here, 20 minus 10 is 10. So 10 and 10 definitely add to 20, and then they maximize the profit. 10 times 10 is 100. Say I had 19 and 1, the product would be 19. If I had 9 and 11, the product would be 99. So this maximizes the profit. All right, next one. A rectangle is to be inscribed under one arc of the sine curve above the x-axis. What is the largest area a rectangle can have, and what dimensions give that rectangle? So we always want to try to figure out what's the necessary info, what are we looking for. So that first sentence is going to help us draw a picture. We definitely need that. What's the largest area? So that is what we are trying to maximize. And then when it says what dimensions, that's the answer that we're actually supposed to be giving when we're done. Okay, so let's start with the mathematical model, which includes a picture. So a rectangle is to be inscribed under one arc of the sine curve. Okay, so we know a sine curve starts here, it goes up, it comes down, and then it would go back down below the x-axis, but I just want one arc. And so we've got a rectangle that's going to be inscribed under one arc of a sine curve. Okay, so it looks like that. So what we're trying to do is we're trying to maximize the area. Okay, so we want to maximize the area formula, and area is base times height. Okay, so here is what we are trying to set up. We know that the height is going to be given by whatever the sine of x is. So like, let's take this for example. Let's call this some random value x. Okay, so if that's some random x value, this point right here is x for the x value, and then the y value is whatever the sine of x is. All right, and then this, whatever this point is, let's just call this x2, and then the y value would be the sine of x2. Okay, so that's where we are so far. So what we know is that h, the height, it's like this is h for height, this is b for base. We want to come up with a formula for both of those, and the formula for both of those actually we want to be in terms of x, since the function all has to do with x. So the height is going to be given by the sine of x, whatever the sine of x is, and then the base, and now this part gets a little bit tricky, because I can't just do x2 minus x1. We don't know what x2 is, we don't know what x1 is. We want them all to come back to the original variable, which is just an x. Okay, so now here is the part that's a little bit weird, and this all has to do with the sine curve. It has to do with some of those properties that we know. So like this one right here, if I know that this guy and this guy have the same y value, which they do because it's a rectangle, and so we know that they have to have the same y value, this x value right here is going to be pi minus x. And this is something that, this one's a little bit trickier. It would be pretty difficult for you guys to come up with this on your own, but we're doing it together, so we can talk about it once we get it set up. Say that, I had this point right here and this point right here. Think of two points that have the exact same value for sine. Let's take, like pi over 6 and 5 pi over 6, for instance. Pi over 6 and 5 pi over 6 both have a value of sine of 1/2. And 5 pi over 6 is pi minus pi over 6. Let's take pi over 4 and 3 pi over 4, for instance. They both have a value of sine of root 2 over 2. The second part, 3 pi over 4, is pi minus pi over 4. So if these values of sine are the same, that means the x values add up to pi. Pi over 6 and 5 pi over 6. Pi over 4 and 3 pi over 4. Pi over 3 and 2 pi over 3. So if the value of sine is the same, the two x values add up to pi. So if we call the first one x, we have to call the second one pi minus x. Okay, so now the base is pi minus x, this quantity right here, minus x. Just a quick little distance formula. This x value minus this x value, which comes out to be pi minus 2x. Okay, so that's where we're at so far. We've got the base, we've got the height. Now we're going to plug it back into my area formula. So base times height. Okay, so now that is a formula that is all in terms of one variable. We have to get our formula all in terms of one variable. Okay, so now a domain, before we go any farther, when we are talking about x, x has to be somewhere in this region right here. Okay, so I suppose the smallest it could be was 0. It's not going to actually be 0 though, otherwise my rectangle would have no height. And then I can go all the way to here, which if you're picturing a sine graph, that point right there is pi over 2. So we can go all the way to pi over 2, but same thing, it won't actually be pi over 2, because then it wouldn't be a rectangle, it would just be a line. Okay, so that's where I'm at so far. I've got the function, I've got the domain. Next thing I'm going to do is I'm going to identify the critical points. And I find critical points by taking the derivative and setting it either equal to 0 or where it's undefined. So here I'm going to do a little product rule. So the first, which is pi minus 2x, and then times the derivative of the second, derivative of sine is cosine, plus the second times the derivative of the first. And the derivative of the first is a negative 2. Keep in mind that pi is just a constant. Don't let that freak you out. Okay, so there's not going to be any place where this is going to be undefined. Polynomials are never undefined. Cosine and sine are never undefined. So I just want to know when this thing is equal to 0. Now this thing, looking at this, very solvable. Looking at this, not so solvable. So what we're going to do is we're just going to plug that function right into the calculator and we're going to solve. So, if you're on the Inspire, open up a new document, graphs page. So we're going to plug this function in. So in parentheses we have pi, and the pi is down by the h. Pi minus 2x, and then times the quantity cosine of x plus negative 2 times sine of x. Okay, so graph that, and then I know what my domain is. I know where my restrictions lie. And so when I'm looking at this whole giant graph, I might as well restrict my domain. So we've talked both with the Inspire and with the 84 how to restrict your domain down. On the Inspire, you hit the menu key, and then there's this whole window zoom menu. If you're on an 83 or an 84, the window zoom menu is just right in the top row of those gray buttons. So we change the window settings. I'm going to change them to 0 to pi over 2. And again, the pi button is down by the H. If you're on an 83 or an 84, the pi key is above the caret. Like if you look at multiplication, above that is division, above that is the caret key. You have to hit second and then the caret key to get pi. Okay, so hit enter. So I look at just this one little picture right here, and there's only 1 0. And this is definitely a max because if I'm looking at my derivative goes from positive to negative, which means my original function goes from increasing to decreasing. So I want to get that exact value, so I hit menu, analyze graph, and then I want to find that 0. So we practiced this a little while ago. You click to the left of it and then drag it over to the right, and you end up finding your value. Okay, so that comes out to be 0.71. The last digit actually is a 0 if you were looking at the 83, which I'll show you everything on the 83 as well. Y equals, so we've got pi minus 2x, and then the cosine of x plus negative 2 times the sine of x. Okay, so if we change this window, 0 to pi over 2, we're looking at the very same window here, the very same graph. We're going to find that 0 as well, and you can see what all the digits are this time. So if we go for the 83 and 84, we hit second and then trace, which takes us to the calc menu. We're going to look at 0 here as well. We want to get to the left, which means we want to get above the x-axis, hit enter, and then go to the right of the 0, so we end up down below. Okay, so we've got it does end up being 0.710. And I've had people ask me this on the AP test before. You do actually want to keep that 0 if you're writing down. So x equals 0.710. And for us, to get as accurate as possible, we might as well write down all those digits. So now that will make our answer as accurate as we possibly can. All right, so that's our value of x, and x does fall within the domain because pi is 3.14. So pi over 2 would be about 1.57. So it definitely is within that domain. The last thing, so we found the max, and we were looking at a picture, and we saw that the derivative went from above to below the x-axis, so we know it's a max. The last thing is we want to interpret and answer. The interpret and answer step basically means make sure you're actually answering the question that was asked of you. So it says, what is the largest area? We're not looking for the x value, we're looking for the largest area. And so we want to actually plug that x value into the area formula, which is right here. Okay, so if I go right here, let me show you kind of a weird little trick with this one. So say I have this value right here. If I second quit and go back in here, the second that I hit this store key, storing as x or something like that, it actually remembers that 0. So you can't hit anything else in the meantime. You have to go right back to your main screen, and the Inspire will actually do that as well. But now I have this exact value, and I can use every single digit to be as accurate as possible. So let's plug into this area formula right here. So in parentheses, we've got pi minus 2 times x, and I can just hit the x, and it automatically inputs that in, and then times the sine of x, and then same thing, it automatically inputs this value for x. So hit enter, and this is what I get for my area, 1.122. And then no units were given at all, so I really don't have to give any units in my answer. And then it says what dimensions gave that rectangle. So dimensions, I know that my x value was 0.710, but that's not what we were asked for at all. H is the height, so we want sine of that x value, and the height is about 0.652. Times, and then the width is the x minus 2x, or the pi minus 2x. And again, every time I hit x, it's plugging in my value of x that I stored. And so this is 1.721. So So again, please make sure that you're actually answering the question. That's what I mean by that last step. Okay, let's see what we've got on the next page. The next page we are going to do one example from business and industry, and then we will do the fourth example together in class. Okay, so examples from business and industry. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin, and then bending up the sides. So we're going to get a nice picture for this one. Okay, so let's start with a 20 by 25 sheet or inch sheet of tin. Okay, so let's say this is 20. Now this looks more like a square. So 20 by 25. What we're doing is we're cutting congruent squares of side length x. So you cut out a square here, and then they're all going to be the same size because it's all side length x. Okay, so all of those side lengths are length x. All right, so we've got that set up. Now if we read through the second sentence of the problem, here's what we're trying to find. So this right here, we're going to cut those out, and then what you end up doing is you fold along this line, you fold along this line, fold along this line, and then these rectangles right here end up being the sides of the box, and then this piece right here ends up being the base of the box. So picture it, try to get a nice visual. You do end up with an open top box. All right, it's like the bottom of a shoebox or something like that. Okay, then it says, how large should the squares be? So we're trying to solve for x. How large should the squares be? So we're trying to find what value of x to make the box hold as much as possible. Okay, so to hold as much as possible, we want to maximize the volume. Okay, so we want to maximize the volume, and we know volume. Volume is length times width times height. All right, so let's come up with that function. Length times width times height. The length, let's say, is this measurement right here. That will be the length. So now the length was 20 inches. 20 inches was the original, but then I subtracted x here, and I subtracted x here. So my length is 20 inches minus 2 times x, because there are 2 of these x cutouts that I'm making. This is x, this is x. And then my width will be this length right here. I guess really just this length from here to here. And so my width used to be 25, but I subtracted 2 of those squares. And then my height is actually just going to be x, because when I fold up all those corners, my height will be whatever that cutout x was that I made. Okay, so that is my volume formula. I actually do want to FOIL it out and simplify everything up. Okay, so I'm going to start by foiling these 2 out. So 20 times 25 gives me 500. And then 20 times negative 2x is a negative 40x. Negative 2x times 25 is negative 50x. Negative 2x times negative 2x is a positive 4x squared. And then I have this one remaining copy of x that I'm going to multiply everything by. So I'm going to combine these 2 middle terms and then multiply everything by x. So 500x. These 2 combine to a negative 90x, and then multiply by 1 more x, and then this would be a 4x cubed. Okay, so that's my volume formula. There it is. Got my function, I've got my quote-unquote mathematical model set up. Next thing I'm going to do is identify the domain. Okay, so the domain for x, picture what x can be. I definitely can't cut out a negative side length. So the least I could cut out would be 0. I use parentheses because you don't include the 0. You can't cut a side length of 0, otherwise it wouldn't actually be a box. And then the most you can cut out is 10 inches. Think about that. This side length right here is the shorter of the 2. 20 is shorter than 25. And if I'm cutting from this side and I'm cutting from this side, I can't cut 20 inches because I have to cut 2 of these. So I could cut 10 inches from both sides, not including 10, and then I would have like the teeniest little length. All right, so technically I could go anywhere from 0 to 10, not including 0, not including 10. If I cut out like 9.9, then I'd have the teeniest little strip left to be my length. All right, so that's my domain. Then I know if anything that falls in there is feasible. Next, I'm going to find my critical points. So I'm going to take the derivative of the volume function. So 500 minus 180x plus 12x squared. Okay, so first thing I'm going to do is I am going to factor that down. So all of these, like 12 is a multiple of 2, 3, 4, 6. 500 is a multiple of 4, but not of 3, not of 6. And 180 is also a multiple of 4. So I'm going to divide out of 4. While I'm doing that, I'm going to put it in standard form. So 12x squared, if I divide out of 4, I get 3x squared. 180, if I divide by 4, I get 45. And then 500, if I divide by 4, I get 125. So this is my volume formula. This is not going to come out nice and neat, but we do know how to deal with quadratics that don't come out nice and neat. We can take the quadratic formula. So if I want to solve for x, because I'm trying to set this equal to 0, it's not undefined anywhere because it's a nice neat polynomial. So I get negative b, so that would be positive 45, plus or minus the square root of b squared. So 45 squared, and plug that into the calculator, comes out to be 2,025. And then minus 4 times 3 times 125 gives me 1,500. And then all over 2a, 2 times 3, of course, is 6. So I'm going to plug that stuff all in. So we start with 45 plus the square root of 2025 minus 1,500 over 6. And that gives me 11.319. And then next I plug in parentheses 45 minus the square root of 2025 minus 1,500. And then divide that by 6. And so for that one I get 3.681. Okay, so those are the two values I get for x when I do the quadratic formula. Keep my domain in mind. I can't possibly cut out squares that are over 11 inches long, because otherwise I would run out of room here on this shorter side. So this is my only critical point. You always want to check that it's actually going to maximize the volume. And so we do a little sign chart for v prime. Use this value of 3.681. So say I plug in something like 1 into this function right here. I'm sorry, this function right here, my derivative. 500 minus 180 plus 12. That comes out to be positive. And then say I plug in something bigger. I could plug in something like 9. I am bounded on the ends here by 0 and 10. So I could plug in something like 9. You might want to plug that in. 500 minus 180 times 9, and then plus 12 times 9 squared. So that comes out negative. So here's what's happening. As I go from 0 up to a square of 3.681, my volume is increasing. Then from 3.681 down to 10, my volume is decreasing. Because the derivative goes from positive to negative, that guarantees that this actually is a max. So you do need to do that at some point, because a critical point might turn out to be a min. So then we'd be in trouble. Okay, so make sure we are actually answering the question. So how large should the squares be? So the squares should be 3.681 by 3.681. Those are the dimensions of a square, of course. And then the volume comes out to be, now I'm going to plug that into this volume formula right here. So I've got this value. I'm going to store that in as x, so I get every digit possible. And so I plug in my volume formula. So 500 times x, and remember it uses that last value, minus 90x squared, and then plus 4x cubed. So I get 820 and then 0.528. Whenever there are units, we want to give units. So this is 3.681 by 386.1 inches, and then volume ends up being inches cubed. All right, so that answers my optimization question. Again, the most important thing you can do with these is make sure you're actually answering the question. All right, so we're going to do example 4 together.